Good afternoon, everyone. My name's Stu McKenzie. I'm the Science Manager with the Criminal Investigations and Network Analysis, or CINA Center, here at George Mason University. Thanks for joining us remotely today as we continue our series on bringing university-based innovation to bear on the challenges facing federal law enforcement. As we're convening exclusively on WebEx today, please do mute your microphones if you'd be so kind. As always, we'll have a question and answer session at the end of today's talk. And if you have a question, you can type it in the chat box on the right-hand side of your WebEx screen. We'll respectfully direct those to Dr. Seshaiyer at the end, although he may field one or two as he sees fit during his talk. Before we begin, please do mark your calendars with our next talk, which is on May 14th, when Dr. Jody Quass will explore methods for investigators to enhance disclosures in victims of sex trafficking. To register for Dr. Quass's talk and other upcoming events, please see our website. If you're not already on our mailing list, do shoot one of us an email. We will be more than happy to make sure that you're kept in the loop. This afternoon, however, I'm delighted to introduce Dr. Padhu Seshaiyer. Padhu is a tenured professor of mathematical sciences and associate dean for academic affairs at George Mason University's College of Science. He also serves as director of both the STEM Accelerator and of COMPLETE, that's the Center for Outreach in Mathematics, Professional Learning and Education Technology. He is a highly regarded and prolific expert, not just in computational mathematics, but also in scientific computing, computational biomechanics, and STEM education. Indeed, a full description of his accomplishments would probably take this whole hour, but he's been kind enough to share with us today some focused insights of a special relevance to the Homeland Security enterprise. The title of his talk today is Computational Mathematics for Solving Global Challenges Involving Criminal Activities. Padhu, we're just delighted to welcome you this afternoon. Thanks for joining us. And with your permission, sir, I will hand off to you for your presentation. Thank you.
Thank you very much, Jim. And thank you, everyone, for joining. And I'm just going to share my screen. I'm assuming that you can all see my screen. Okay, great. So I'm looking forward to this talk because I have been spending my last decade, after I became a full professor and on specifically engaging students, faculty, and teachers and people at all level about the importance of mathematics in solving real-world problems. And solving crimes is one of the most important real world problems among so many other things. So, and the interesting thing is how can we use all the mathematical tools that we are teaching and or also engaging in research, and how can the students actually make meaning of the mathematics that they are actually learning in the classroom. And so I hope to share some of my work with different stakeholders. And when I said different stakeholders, all the different groups that I've had the opportunity and the privilege to work with. The top left here, working with students in active learning, getting them in front of the board and having them, publicly share what they think about their ideas first, and then trying to help them grow their ideas. And then, of course, working with a wonderful group of people from the military who are always engaged in fun problems that turn into, of course, they are very serious, but how that you can actually use, say, things like calculus for understanding how to solve problems in the field. And then a group of students on the right, top right, which is a group of students involving graduate, undergraduate, and high school. So that's what is interesting about this picture is the fun that I have when I work with multiple groups of students, everybody mentoring each other also, and that peer learning is very powerful. And then to the right in the middle, I have a group that I enjoy working with, just teachers. And so every summer and all through the year, we engage teachers in enhancing their pedagogical practices so they can actually go back into the classroom and try some things to different in their lessons and how children actually respond to make the mathematics more interesting and meaningful. And I will talk more about the picture in the bottom where I'm standing with the student and Senator Mark Warner. And this has to do with a project involving crime. and how he was so super excited to learn about it. And I will share when I talk about that project. And then comes to one of my biggest passions is a program I co-founded with a couple of my colleagues at Mason. It's called Focus, Females of Color Underrepresented in STEM. And it brings close to 100 girls, middle school girls to campus, and then about 30 high school girls to campus, and who are all engaged in a whole week of STEM. And the high school girls are engaged in research, and they start very early, and that's the whole idea. And then, of course, we engage with undergraduate scholars. And so in the back, when I do research and teaching, I want to make sure that all those are integrated with activities that we can create to build the next generation workforce, competent to solve real world problems, and expand the opportunities to women and underrepresented minorities. And being a former program director at the National Science Foundation, this was a top on my priority also. And I also serve as the national chair for the Society for Industrial and Applied Mathematics Diversity Advisory Commission. And so this is something that is not just at the high school or the middle school, and it's all the way up to graduate school, faculty, diversity, inclusion, access everywhere. And then, of course, on the left is teachers working inside the classroom and as students, and engaged in activities. On top of that, there's my partnership with global partners, and that's a country where I engage with the students and the teachers. And I created a concept called STREAM, which is STEM, we all know as science, technology, engineering, mathematics. STEAM, we all know as science, technology, engineering, arts, and mathematics. Now, STREAM, the R stands for readings, or you can think of it as writing without the W. And so imagine having, we stream videos, we stream audios, we stream movies. Why don't we stream education? That was a simple concept. And so this country has not only taken that concept to heart, but recently, just as 2 weeks old, the Minister of Education has decided that stream will be the way all the children in the country will be actually exposed to learning in the next few weeks due to COVID. And they are going to be presenting all the lessons, all the activities we created on TV channels. So there was a crime-related project also I worked with there, and if I have time, I can share that. So that's so. As I said, my goal is to work with all stakeholders, and I saw from the group of people that are registered for this talk. It's everybody from academicians, non-academicians, from companies, industries, K-12. So this is fantastic that you're all here. And so I will try to share my viewpoints all across, so this way everybody gets some benefit out of the talk. So I do want to definitely recognize several key stakeholders, the National Science Foundation, where I personally worked as a program director myself at some point, and the Virginia Department of Education, who have been very supportive in my efforts to create new program activities and involving important subjects or topics that must be included in the curriculum in some fashion. For example, computational thinking or mathematical modeling. These are not explicit subjects, but if you can start to integrate these things into the K-12 classroom, then the students will be well prepared when they come to college, and then, of course, later on, when they start to become faculty or go towards a company. CUR stands for the Council for Undergraduate Research. So that's very, very important after the students come to college, what type of problems they can engage in. And 4VA is a united front of multiple colleges working together in Virginia to attempt to solve challenges. So, and then of course the Department of Defense, who have been supportive in some of the programs that I've been coordinating, and I'll explain how they have contributed in terms of the problems that I've worked on, and the National Academies of Science, Engineering, and Medicine, which I serve on for mathematics instruction on a commission. And and also was able to be involved in a global project that involved crime. And I will talk about that later also. And that was through the Nelson Mandela African Institute of Science and Technology, which is the symbol that you see in the bottom, which is where I'm also a faculty. Of course, I do reside in the College of Science as a professor in mathematical sciences, and then I work with several countries in Latin America, and I actually see some names of people that are already on the call. So this is great that you're all able to chime in. So that's great. Well, before I start, I do want to say that mathematics has this negative connotation sometimes for most people, probably because at some point they learned it in a way that which was not meaningful to them, and at some point, it becomes fear. Fear becomes hate when they come to college, and then all of a sudden, I don't like math. So it goes from this phase of a fear to hate, and then not liking. So and so my goal has always been to change that attitude, and but the way we can do this is not to force the students or faculty or whoever is not liking math, but to actually work from their perspective. What do they like? And then bring the math out. And that's how I've been working. And but what I've been noticing is if you can do that, if we can educate as educators do that, we can not only help them make the mathematics meaningful, but actually mathematics can make impact and help in policy decisions. So what you're seeing in this picture on the top left is the former governor of Puerto Rico, and I'm standing with my students there and the faculty at the top right. She's from Puerto Rico, and together we worked on a problem, which I'll talk about later on, which helped understand spread of gangs in Puerto Rico. And then the kids are, of course, presenting their work. And then not only that, and these students were able to take it back into the focus program and engage the students, the girls in the focus program, to actually, enjoy their learning, at the same time learn some math and other aspects. So this to me is learning by doing. So if you miss some of the aspects about my educational philosophies, you're welcome to always, check out my TEDx talk, and where I talk more about my perspectives on teaching and pedagogy. So this talk had the title Computational Mathematics. In fact, that was one of the programs that I was the program director for at National Science Foundation. And that picture pretty much summarizes it. We are going to talk about some physical system. This could be a tornado, or it could be COVID, it could be whatever is the physical phenomenon that's going around us. And then we want to help translate that into a mathematical model. From a model, then you try to see if there are textbook solutions, which is what we call as analytical or exact solutions. If you can't find it, which is what happens in most of the cases, then you try to find a numerical solution. That means on a computer, try to write a program, try to write on a calculator, for example. Now, one of the most important things that we not forget is there are also people doing experiments. And so again, I'm taking COVID as an example. You could get lots and lots of data that you're seeing, but then how can you actually make sense of the data and make predictions and use those predictions to get ready? And this is also very important in crime. So we will usually, the way we work in computational mathematics is we look at the phenomenon, come up with some kind of a compartment or some kind of a model, which is more like a picture. And then we translate the picture to equations. Then the equations are solved, and then we get some graphs. From the graphs, we are going to predict certain things. So you're all probably hearing this term R naught, or basic reproduction number, in terms of COVID, which is nothing but how fast it spreads from one person to multiple people and things like that. So here is an example of one infected person giving the disease to two people. So you can kind of relate that to the basic reproduction number and things like that. And then from there, we have lots and lots of data generated from different places. The next thing that you need is some kind of a neural network, to actually be able to predict this for a longer period. So this predictive capability of the models that we create is one of the big reasons why, many of the problems can be handled much earlier. And then, of course, this can be applied to real world problems. So for example, I have done work on computational biomechanics, which is on the top left, you're seeing like a brain aneurysm simulation. And then in the bottom, you can think of like, for example, a tornado coming and pushing a building, and it's creating these secondary vortices and things like that. And then, of course, this simulation involves deep learning with, flow across an obstruction and things like that. So that's the modeling and simulation. So let me switch my towards how does this all apply to crime. Of course, when you think of crime, there's different types of crimes. Of course, I just wrote down the few of them that we are all aware of, the personal types of crimes, everything from assault to hatred to arson to child abuse to domestic violence to kidnapping and rape. Then there's the property type crimes, everything from robbery to larceny to auto theft to shoplifting and so on. And then you have the inchoate crimes, which is like aiding someone, or it's more than the intention to actually commit a crime. So the conspiracies that people get involved in, or statutory type of crimes, which is like, say, DUI, driving under influence, or minors possessing alcohol, or selling alcohol to minors, or drug crimes, for example. So those types of crimes, and even public intoxication, all that stuff. And then you got the financial crimes, which is like the fraud, the blackmail, the embezzlements, the tax evasions, the money laundering, and so on. And then there's cybersecurity crimes, everything from even virus being spread across the internet and things like that. So these are different types of crimes, and I will give you examples of some of the specific ones that I've worked on. Before I do that, though, my classes are always based on participation. So what I want you to do is to think, text, and reflect. Okay. And here's what I need you to think about. I want you to think about what are some of the fundamental competencies now that you know all these different crimes, criminal activities, and more that are out there. But what do you think we need to prepare? So if you're a teacher, think about what competency should they have. I just don't want a big essay, just a couple of words or one word. What competency do you think the student should be having to solve these problems? If you're a faculty, what type of research, what skills do you think you need to give your students? If you're a person from, say, Homeland Security, who would you like to hire from your side? What competency are you looking for in your side? And so on. So based on what your background is, please chime in, go into that website. It's also on the text box. And I will also showcase something in just a second. It's going to be a website, which I'll share with you all. And what I want you to do is just go to that poll website and start typing uh, whatever comes to your mind. So somebody has already typed something, and that says critical thinking. That's a great one to actually have in terms of typing. So go ahead and take your cell phone or take your whatever technology you have, and oh, there it is, problem solving. So what you're seeing is real time. Oh wow, you guys are really fast, amazing. So I see critical thinking, problem solving, cultural, domain expertise, analytical, and knowledge. So the word knowledge is very big on the screen because multiple of you are typing knowledge. And oh, thinking, that seems to be a very important thing. That's fantastic. So keep typing. So along with this lecture, I hope you learned about a new tool today, new technology tool. It's called Poll EV, or Poll Everywhere. I use this in my classes to poll students to do like a pre-assessment on assessing the knowledge they already have, so I can gear my lectures to exactly what they already know and what they're thinking. Data, that's coming out really well. Okay, so that means lots of you are thinking about data. And keep typing, and this is fantastic that you're typing, because this helps me to build. So remember, you're thinking about the knowledge that the students or the from Homeland Security, who are you looking for in terms of hiring and things like that. So that's it's great that you're looking for. If someone can mute their mic, that'll be great. And so that's great that it's real time and you're able to see what's going on. And it's beautiful because it's the community that's watching my talk right now and your viewpoints. And I like the word bias that's hidden there. Implicit bias is super important. The bias that we bring into problem solving is very important. Detail oriented, that's really important. Some of you are very detail oriented. Some of you wanted collected skills, and so on. So this is great that you are actually typing, lots and lots of things real time. Um, and I wish, we had all the time to keep seeing this wonderful screen. But I promise that after the talk is over, I will collect all your input and I'll add it as a slide and you can see for yourself. But I guess we all understand what this software can do, the tool can do. So I urge you to use this in your classrooms, use this for workforce. If you're working in any of the industries, this is a fantastic tool to use to learn about what student or what your workers are thinking and so on. Okay. So one of the important things I wanted to point out, I noticed is several of you pointed out 21st century skills that our students or your workers need. Communication, not just sit in cubicles and just do their own part, but be able to articulate what they are thinking. This is super important when it comes to solving big challenges. Communication, collaboration, creativity, which is very, very hard. Creativity is super important when it comes to solving criminal problems and things like that. Critical thinking too. uh, Frameworks. And since there are many educators here, I want to make sure there's so many ways you can engage students. Everything from experiential learning, taking them outside the classroom, to having things inside the classroom with the collaborative learning. So of course, the challenge is, as educators, we need to stop talking less so the students can talk more. This is, by the way, the philosophy of one of the top countries in education. If you go to the Ministry of Education in Singapore, the slogan is teach less, learn more. We should teach less so the students will learn more. That's the philosophy, and that can apply to workforce too. And then I'm going to focus on challenge-based learning, where I'll introduce two of the things that I use in my classes. I've been using this for years. This is the United Nations Sustainable Development Goals, and the National Academy of Engineering Grand Challenges, and I'll tell you how that applies to crime. And of course, make your curriculum project-based, engage them in active learning to have them do learning by doing. Why is this important? Because it is very important for us to start moving away from the frame of teaching students to test to teaching students for life. What do I mean by that? Well, we want to focus not just on content. I'm not saying content is not important. Content is super important. But as important as competencies is trying to figure out, and this is something that many of us, many are not very well trained to do. So, yes, if you just train people on content, whether it's the workforce or the education, you're just going to get them to think about discipline specific topics. But if you train them for competencies, you're not only doing discipline based skills but also transferable skills. This is very important when it comes to upskilling and reskilling. And so they develop all the things that you guys said: digital, data. I saw all these words come out in your things. So while there is collaboration, communication, critical thinking, creativity, and citizenship, 5 C's, I created my own 5 C's, which I have a paper that I've written about, which I'm happy to share for the educators if you're interested. You always start with the context, and these contexts could come from different bigger frameworks. And crime could be a great context that sets up a real world problem. Now, from the context, we create a curriculum. Curriculum maps, what do we teach? What's the input? What's the outcome that we are expecting? And things like that. From that, we develop the content. This is where the subject expertise will start to come. Now, by the way, if you're in workforce, it applies to you also. And the content then leads to concepts. How do we present that information? If you're an educator, then it's about the pedagogical skills and competencies that you can bring into the classroom. Okay, just because you're a great teacher, there's always scope to learn, to incorporate new ideas and all that stuff. And that is how we build competencies, whether it's for students or workforce. Now, I said the context. The context, of course, can be from one of the things I've been teaching for 3 years or 4 years ever since this was introduced, is the United Nations Sustainable Development Goals. I do want you to see goal number 16 applies to crime, peace, justice, and strong institutions. And if you have the time, you should go in and see how they have laid out this Sustainable Development Goals with 17 goals, with 169 indicators, and then several targets to actually identify each one of those goals, what should be done. And I have some colleagues and I see they are also online who I work with closely, and we have actually identified, for example, good health and well-being. COVID-19 appeals to this particular thing, and you can go and read the target. So we just wrote an article on COVID is not just impacting number 3, it's impacting all 17. So if you're interested in that article, please let us know. We'll be happy to share that also. Now, of course, as I said, peace and justice and good health and well-being. I'll combine these two later on. Now I'm going to switch gears, to asking you to think about the following. So, if you look at these, and you're welcome to type on the chat box, and I'm going to pick up the chat box here so I can actually see what you're typing. I'm going to bring the chat box. So go ahead and type the movies that you see on the screen. What movies are you seeing? Do you recognize any of them or TV shows? Numbers. Okay, Alexa sees numbers. Okay, Contact. Very good. Chris and Franny, that's great. Contact. Da Vinci Code. Okay, I see Da Vinci Code. Very good. So wonderful and Beautiful Mind. Yes, Beautiful Mind. Great. But then you guys did not guess the obvious one. The obvious one on the right, which actually has the name of the movie, which is 21. That's exactly right. So I want to tell you something about these movies. What's interesting is this obviously math used in several movies, but these movies involve crime in it. So I just want to point out some of the interesting things. On the top left is a 1997 thriller where a Contact, that's exactly right, where Jodie Foster actually acts as a scientist that discovers an alien signal. But the interesting thing is the alien signal is composed of prime numbers. So it's a way to actually talk about prime numbers. Now, next, right after that is actually the Da Vinci Code. Of course, Da Vinci Code was a mystery thriller. The novel was probably much better, and it surrounds a murder in France and cryptic clues in some of Da Vinci's most famous paintings, one of which you see in the back, Mona Lisa, that leads to like the discovery of a religious mystery that's protected by a secret society, like, really fun stuff. But then among these things needed to decode this secret message is they had to recognize the Fibonacci sequence, its connection to the golden ratio, and then its connection to the pentagram. And so there's lots of cool mathematics that comes in. Now, another fact that you may not know, Dan Brown happens to be a very good author. And if you did not just type Dan Brown in geometry, one of the best geometry textbooks high school geometry books comes up. Okay, so, and it's a really comprehensive textbook. There's a little fact that you may not know. And on the top right is 21. This is it's a fact-based story. 6 MIT students who were trained to become experts in card counting, which of course is illegal. And subsequently, they actually they took Las Vegas casinos for millions. And that's what the movie is about. Of course, there's some things in the movie that is not true, but Kevin Spacey acts as the unorthodox mathematics professor, leads the team. It's a fun movie to watch, and together the students and the faculty, they start to become very good at counting cards and to improve probability of winning the card game at blackjack. That's the whole movie. And then, of course, to the bottom is Russell Crowe, and who won the Oscar and for being, portraying the movie portrays a mathematician. So it's not a film about mathematics, but it's about the paranoid schizophrenia that the mathematician goes through. But a lot of people don't realize the power of the Nobel Prize winning idea that he had, which is now called the Nash equilibrium, and which uses something called game theory and but the movie depicts something like graph theory and cryptology to break codes, which is some things he did, but his main contribution was to the economic aspect of it. And then, of course, the popular TV numbers. I saw one person actually. It's about the FBI agent Don, who's standing on the right, and who basically hires his younger brother, who's respected genius in mathematics and a college professor, and to try to solve crimes actually. So, and they talk about episodes where the first one had to do with the serial rape incident in Louisiana, and then it was followed by a episode with lots of bank robberies and things like that. So I want to just tell you all the connection to these things, and this is great. And I want to take like 1 minute now because all my classes involve quizzes. So like every good teacher, I'm going to showcase this quiz, and I want you to type as many movies as you can think of. These pictures tell you. Go ahead. Let's see how good your movie sense is now. So I'm trying to. Oh, American Pie. Andrew was just quick to see row number 1, column number 2 is American Pie. Oh, floor 13. Andrew, very good. It's actually the 13th floor. That's the name of the movie. That's in row number 2, column number 4. Very good. Matrix. Lux actually sees a row of numbers, columns, and that's an array, and that's a matrix. Bala says Life of Pi, and that's actually American Pie. So, okay, you see the pie, that's great. If you can see the life in it, that's actually even better. The Exorcist too, that's fantastic. You saw the X and you saw the symbol or and then the cyst. Alexa, Mean Girls, fantastic. It's girls on the top right that's being added and then averaged. That's average is a synonym for mean. So Mean Girls it is. Andrew is fantastic. You guessed Green Mile. You not only guessed 1609.344 is a mile, you guessed it's green. That's somebody won the best supporting actor. So why I'm giving this is because to differentiate from the last one I gave you. The last one's, oh, Lux, fantastic. You must be very good in calculus. So S stands for displacement. This is the movie right at the bottom. And DSDT stands for velocity. When you take the magnitude, it actually is speed. Sandra Bullock and Keanu Reeves. So David, fantastic. You recognize not only the movie, but you recognize the number E right next at the very end, 2.718. That's the number E, exponential, and behind is a wall. So wall E it is. Now, why do I, and now let me disclose all the others too. So you can see, let me go through the movies. On the third one is actually a sine wave. There's a bunch of them. It's Night Shyamalan's second movie after Sixth Sense. It's The Signs. The I in the second row is in golden, so it's James Bond Golden Eye. Once you understand the summation symbol, it's the sum of all fears. That's what that second row is. 13th floor, somebody already found out. Exorcist, fantastic. This is a city under a sine wave. It's called Sin City. This, I was hoping somebody will catch it. It's the social network. And then 2 times the number, of course, is even. So 2 times the number plus 1 would be odd. It would be the Odd Couple, an old movie. E to the I pi plus 1, ask any mathematician, they'll say it's a beautiful result in mathematics, combined with the number of the beast. It's the beauty and the beast, okay? So, and this one, of course, I always have something hard. This is the heat equation. So just to clarify, just so that you movie buffs out there, just to make sure that you recognize this. Now, the reason I did this is for several things. I showed you a picture of movies with people's faces and you were able to somehow recognize your mind worked in a very different way. Now, when I show you symbols, you start to look for patterns, you'll start to look for content knowledge that helped you to actually, looking at the or symbol and you put together, it's like solving a crossword puzzle. In a way, when we solve crime, we need to have these types of competencies also. Of course, one person here recognized this number as E. And if I ask you what is E, you're going to be like, wait, can you show me the slide again? No, I'm not going to show you, but I'm going to ask you to remember the following. There's only 2 things you need to know about Andrew Jackson. He was the 7th president of the United States. He was elected into office in 1828. I repeat, 1828. Like every good mathematician should know, the angles of an isosceles right-angled triangle is 45, 90, 45. Like I said, you just need to know 2 things about Andrew Jackson. I just told you the digits of E through a story. So sometimes when you want to solve crime, you want to think about a story behind it. And that's exactly something important. I know that I've talked enough, and in terms of getting you warmed up, I'll take maybe the next 20, 25 minutes to wrap up my talk in actually talking about specific projects, okay? So I'm going to go through different examples of some of the projects that I do, and then also finish with some human-centered approach to problem solving. So I'm from Virginia here. I live in an area called Chantilly in the Loudoun side, and then there's Chantilly in the Fairfax side also. This is North. So let's to take my first example, the map of Virginia, of Northern Virginia, specifically that. So the red dots that you see there, I'm just going to, think about, or suppose we know that those are places where some crime has happened. Catch the criminal. So, one of the first things, so, we do just know the locations of the crime, but how do we go about catching the person here? So one thing is to look at patterns, and, you may say, oh, I look for, talk to the neighbors and all that stuff. So as an analyst, what you want to do is you want to look at this and say, wait, do we see any patterns in the crime location? And that can help me to predict when the next one is going to be. So this first approach is going to be to understand where the patterns and crime location is. Unfortunately, trying to go through that process is not exact. It's very random, So because I can say, is this close enough, or is this the path that this person is taking? So instead, if you want to critically think through it, and if you actually start to ask yourself, what if we turn our attention from finding locations to finding where the criminal could potentially be living? Now, that type of thinking is completely different. Okay. So instead of focusing on how the crime is happening to where the criminal could potentially be coming from, now that way of thinking is very, very different. Suppose you were to think about that. So essentially, you want to have the data to think about it. So what we want to do is to somehow come up with some kind of an idea to figure out where could this person be coming from, because we kind of know this person cannot be living too far or too close. So that's an assumption that you can make. And so essentially, what we want to do is to find some kind of a hot zone, maybe a crime zone, where this person is operating from. So in order to do that, or when I say operating from, now I'm going to start using some mathematical terms. Like, I want this to be a high probability region that this person is living there. Then I can do the search there. So what do I mean by that? Well, suppose I were to put a grid on top of my place I'm searching, okay? And then I define something called Pij. That's the probability, high probability that I can find this person in that neighborhood. Let's suppose it's that red box there. So the red box is in the ith row and the jth column, basically. So if I can find probability that this person is in that neighborhood, so then how do I calculate this quantity? That it all comes down to finding that probability. So this is just one approach to actually doing this. So, of course, this is a mathematics talk, so I want to still tell you why there is mathematics in it. So one of the simple ways to think about it is, suppose I'm in the red box, suppose that's where the criminal is. So you can think about how far the criminal, and I'm looking at this second, not the circle that is the first crime spot, I'm looking at the second crime spot, the ones where the two arrows point out. So I want to know how far this person is from that region. So in the x direction, though, if I were to come from all the way from the left, let's suppose that this person is at x sub I distance away, and let's suppose the crime spot is actually x sub n away. Then I can actually find the difference as in the distance in the x direction. I could do the same thing in the y direction too. So now that I know a distance the x direction and distance the y direction, of course, we are going to assume that we are not going to go diagonally because I have to drive through streets. So I'm going to assume that I'm going to go through those distances. When I do that, I can actually come up with a metric, a distance metric that's basically adding up those distances or displacements you can think about. Now, it turns out that this particular context, this formula is actually hidden already. It's a very well-known formula, and it was developed a long time back by a PhD criminologist. And it's a very powerful one, and I'll tell you why it was extremely powerful when it was introduced and all that. And you can notice that this particular term actually appears in the denominator, and it's by the person that you're seeing. His name is Kim Rosmo. It was invented some time back. I mean, here's the idea. I want to still talk about some basic idea about this formula. So you can look at this expression. It's in the denominator, and it's also raised to some power f here. So if you think about it, this is the distance where the criminal is located from the crime spot. So if you actually think about this distance in the denominator, if this distance is, you want to understand, you have to have an idea of where the criminal could potentially be. So if the criminal happens to be far away, now I'm talking about the purple box here. If the criminal goes far away, then what happens to the denominator? The denominator starts to increase. If the denominator starts to increase, then the whole expression starts to decrease because you're dividing by a bigger number. If the denominator, so if the whole thing starts to decrease, then the probability is going to decrease. So you don't want to search too far. Okay, that's what it's essentially saying. But then you can't just, so then the next question is, should I just go really close to the crime scene and search? Well, if you think about it, that's where the second term starts to come in, because the second term has the exact same thing, but it's subtracted from some kind of term which is called the buffer zone. The buffer zone, think of it as a constant which works best, based on past information, data from past information. So this particular thing, what it makes sure is like, the same type of idea, it actually tells you that, of course, if you're coming close to it, this particular thing says, if this term goes up, then the probability goes up. So this has the opposite effect. But then that criminals don't stay right next to places where they work on and things like that. So you want to start thinking what happens. So it's really a fine balance between the first term and the second terms. This is what this formula tells us, okay? Without going too much details into the formula. But so one term starts to take people up and the probability up, and the other one starts to take down as you move to different locations. So notice that I'm moving this square. As you keep moving, it's a balancing act between these two terms that actually calculates this probability. So if you go, of course, too far, like in this picture here, then you're going to go way off, and then your values are again, first term is going to start to act up. So it's a very cleverly computed formula by this criminologist, and it can actually help you to find a crime zone. And I'm going to explain how you can find it. But before I do that, let me explain some more terms in this thing. There is these terms like phi, the B, the G, F. These are, think of it as some weights. These are all just constants that are there. And then, of course, the summation in front. That just means that, well, that's just one crime spot and one grid spot that you're thinking. But I need to cover the entire grids and all the crime spots. So that's exactly why you need summation. So in a way, what you do is you do this for every single grid. So the red square that you are here, you do that, and then you do it for the same crime spot with another grid. You do the same with another grid, and you keep doing this for all the grids and all that stuff. And with all the crime spots, you add them up, you get a probability. Now, those probabilities will give you some kind of a distribution. It's a heat map that gets created. And this heat map can actually help you. In fact, actually, if you focus clearly, let me actually, that picture that you see in the 1980s, I believe, Richard Chase, he was a very prominent American serial killer. And this formula, believe it or not, was actually used to catch this killer. He was not only killing, but he was called the vampire of Sacramento because he was drinking the blood and cannibalized the remains and things like that. But this map actually predicted a region where the killer could have been. Not only did it predict, it actually predicted that purple square is exactly where they found him. So it's such an interesting thing. Not only was it interesting when I learned about it, but also I bring it into the classes. When I was watching Numbers, one of the episodes, look at that. That's the exact same formula. They actually bring this formula into actually solving a murder crime about serial rapists in the episode. So this tells us, something, that's very important. How we can use entertainment to motivate mathematics and things like that. Okay. But I do have to say that there's a measure of randomness here that is very important. And when it comes to humans and randomness, we are probably have so many things that we are good at. One thing we are not good at is at being random. Okay, so in fact, Nassim Taleb was a very famous Lebanese essayist, Lebanese American essayist, scholar, statistician, and he used to be a former risk analyst. That's a statement which summarizes everything. Randomness works well in search, sometimes better than humans. Let me explain. Suppose you ask, in fact, I can ask you all to think about 100 numbers in your head between 1 to 20. If I give you a few minutes to think about or write those numbers in your head, and this was done as an experiment, what was seen that most of us think about numbers 7 and 17 for whatever reason, okay? But we did more than the computer actually did, okay? And not only that, in fact, the study predicted that landmark numbers like 5, 10, 15, 20, we did not guess those things because they were nice for whatever reason. So on the other hand, the computers were completely random, okay, that way. We didn't have any preferential bias to numbers. I mean, like we had, computers didn't have any preferential bias. So if you do the same thing with asking people to put 100 dots on a paper, so for example, humans would do this. If you ask the computers to do it, then they would do things in clusters. So it's very important to think about clusters. And I know that I'm at 12:45. I hope I can talk for another 10 to 15 minutes to give you more breadth on these things. I had a whole bunch of crime problems. I hope it's okay to spend another 15 minutes to get you guys to think about several things. So humans are not random. That's the whole idea. Okay. And so in general, things form clusters. So let me give you an example, another mathematical approach, graph theory. So graph theory is another powerful thing in mathematics that can be used to solve maybe crime problems. So for example, think about social network. Now this picture that I showed you here is more about schools and universities where friends and friends have more friends and things like that. So friending, of course, calls for social networking, which Facebook is the first thing that most people think of. But in fact, through FBI investigation during 9/11, such graphs were very, very helpful to figure out who is connected to who. So, for example, you see the name Mohammed Atta, and I'm going to tell you a story about how graph theory could have been helpful and actually solving something. So, the example before was more about where the criminal lived. The example now we are going to talk about is who is potentially the criminal. That's what we are going to be doing. So think about a simple hypothetical example where I have 20 friends or 20 workers in your company or 20 students or whatever, and they are all clustered by groups. The groups could be based on subjects they like or activities they do together, running they do together, or whatever it is, or in the workplace, concentrating on different things and all that stuff. So, and that's how randomness goes. But the mathematical quantities that I want you to understand here is the ideas that are emanating from that one particular node. These are called edges. Edges are the lines that connect friends to friends. And then each of those black dots are called nodes. These are mathematical terms, nodes, edges. And then how many they are connected to. For example, this seems to be the popular person. He's connected to, say, 7 people. So then we call it the degree of connection. So degree is 7 here. Okay. So the node and the edges and the degree. So how can we use these concepts to actually build something that is meaningful, which will help us with crime? Okay. But before that, I want to explain how some things work. Now look at this guy in the center. Don't ignore this guy, because even though he has a degree of only 1, 2, 3, 4, he may not be the popular guy. Maybe you think so. Think about if I remove this guy from the whole chain, what happens is he disconnects the 3 clusters. So more than this popular guy, this guy is much more important. That's kind of the key here. So it's very, very important for you to understand that. Okay. Let's take an actual example. Suppose there is a rumor going around, and all those red spots are where the rumor is. Okay. All those people know about the rumor, and the rest of them are either know it or don't spread it and things like that. But you as leader of the workforce or faculty, you want to figure out where the rumor started, who actually started the rumor. So who would you go to? Think about it. Well, obviously you would go to the exactly, David. That's fantastic. Betweenness centrality. That's exactly where we are going. I'm assuming that many of you have not heard about this. So we go to this guy because this guy is probably going to tell us exactly lots of things that we can find out. And David has already hit the sweet spot. So suppose the rumor starts somewhere, it goes to all the friends. So let's say it starts here and starts to go to these 2 people, then it starts to spread, and soon it goes through the network and all that stuff. Now, how can we quantify it? So let's suppose that middle guy is called, if we can find, I mean, as I would go and straight ask that person and then backtrack and figure out what happened. Now, if that person were John, and I'm talking about connections between person A and person B, from the picture, you can actually see that I can go from A to B in 2 different ways, 2 paths. But in both ways, I actually have to go through John. So if I were to take the ratio of going through John to the number of short paths, I actually get a ratio of 1. This is what is called as a betweenness, and as David is pointing out. What, on the other hand, if A actually connects with, doesn't have to go through John, it makes friends with C and actually goes to B through C. Now, from A to B, I have 3 paths, 3 shortest paths, but through John, there's only 2 paths. So now John gets a betweenness score of 2/3. So now what you can do is basically try to find these betweenness type a number that corresponds to each one of them. So that's one measure. I mean, this is something so easy for middle schoolers and high schoolers to actually do. Now, we can also think about another one. Let me explain what that fraction that you see there is. Now, if you look at that Mr. Popular that is sitting in the center, that person is connected to 7 red dots. And that's the 7 that you see in my here that are connected through one edge, one red edge, for example. So I'm going to count all the connections that one Mr. Popular has. Well, they have 7 neighbors that are all distanced by 1 edge. Then they have like 3 of them that are distanced by 2 edges. Then they have 3 more that are distanced by 3 edges, and and then you have 4 edges are all the way the 6 people that you see here, the black dots here. And so you calculate that, and you have that as the denominator. That's all the connections. And because there are 20 people, and just like if you know standard deviation, we subtract a 1. We, for normalization purposes, that's where the 19 is. And then if you take this ratio, you get something called the centrality. Again, something that David clarified. So you can, for John, for that Mr. Popular, you can calculate that. For every single person, you can calculate that. So when you calculate this type of betweenness ratios, betweenness numbers, and the closeness centrality score, you can do this for all the nodes, and you can actually do this for lots and lots of people, and you can actually get these scores. And you can go through the entire network to do this. Again, computations that can be given to high school, middle school kids to do this. And if you actually overlay this real data, this is after the fact, if you actually overlay this between the degree and the betweenness and closeness, one particular person came up. It was Mohammed Atta, and he was known to be the ringleader at that in the 9/11 attacks, actually. So just to give you an idea of how something as simple as graph theory can hit something as big and can identify things. So that's the second one I wanted to show you. Watching my time here just to make sure I can give you enough information. So I'm going to kind of go through the next one because I want to get to some other things. The other one is, how now this is about how likely an event is going to happen. So we talked about where the criminal could be possibly be. Second one is more about who could be the criminal. The third one is like how likely an event is going to happen. It could be related to crime again. Say how likely a robbery is going to happen again, and things like that. So there we use another mathematics concept called Poisson distribution. So the distribution is about, it uses simple probabilistic ideas and all that stuff. French mathematician who came up with an idea that a series of discrete events, where there's some kind of an average time that you can calculate between the events, if that is known, but the exact time of the events is not known because it's random, then we can still calculate some kind of measure, probabilistic measure. That's what is denoted here, where the capital X refers to the number of events. You take an interval, maybe it's years, and you can find out how many events happen there. And you need to know what is the average rate at which it happens, and then you can actually calculate, the probability of observing lowercase x events in that given interval. That's what this formula summarizes. Okay, it's called Poisson distribution. For example, if you were thinking about, I just gave a textbook example just for you all to understand. Suppose the births in a hospital occur randomly at an average of 1.8 births per hour. What's the probability of observing 4 births in a given hour at the hospital? Well, you notice that the number of births in a given hour is the uppercase X that you see here. And we're going to assume that the events occur randomly, and then the mean rate is given to be 1.8. And you want to calculate for exactly for 4 births to occur. So you just simply stick in little x equals to 4. And you can calculate this number that gives you a probability. So once you get that, I mean, believe it or not, the first practical application of Poisson distribution was actually recorded by, a long time back. And it was very interesting. It was by Bortkiewicz, who was tasked to identify why soldiers in the Persian army were getting killed, not because of attacks from war, because of horse kicks from horses. So this person recorded kicks of horses for about 20 years in a span from 1875 to 1894, and actually figured out that this was there was an interesting Poisson distribution associated with it, and it was an actual application. So it was great that it's applied to. You can think of like horse kicks being like having some kind of a pattern. If you put on a number line, maybe 2 happen right next to each other, and then there's none for some time, none for some time, and then again it happens, and things like that. If you translate this into a graph, this is what the chart would look like. In fact, this chart actually tells you, something very important. So for example, it tells you, it gives you a nice distribution. It also tells you like where it is most likely that an average number of incidents to occur. That's super important. Now, one thing that the Poisson distribution did not capture well is that the events are, Poisson distribution, the assumption is that the events are independent. Unfortunately, in crime, that is not the situation. It does apply to maybe earthquakes, for example. You could have an earthquake, but then you could have aftershocks, then another earthquake after some time. But even in earthquakes, you have those aftershocks which can be predicted also. So there is some pattern to earthquakes. So people wanted to have a better formula to than the just the Poisson distribution to understand crime or earthquakes and things like that. So now came what is called as the Hawkes process, and it was actually used to study crime, and they had another mathematical formula just like before I was telling you. Every one of these things have some interesting formulas. So the A that you see here is kind of the intensity of the attacks. It's how likely an event is going to occur in a short period. B is kind of the background rate, already something, some randomness that's associated with that, say, crime activity. Now, K is like a kick, for the person to come back and rob you again. And so, but you don't want to keep coming back so many times. So that's why there's a negative decay. That's the same E that you saw before. And so it has to come down as more and more robberies happen, for example. So this is an interesting formula. Again, something easy to compute. For I, of course, the summation here is to add up all these things. So just to let you know, this was an actual formula that was used, and not only was the formula used, there's lots of companies in the US, lots of companies outside that actually turned this formula into iPad apps, and these apps are in cars, and they actually use it for law enforcement, and it's actually called predictive policing. So they can actually identify from the past, the current, from the current, the future, and things like that. So it's a very interesting process. Now I come to what I focus on. I want to take maybe 5 to max 10 minutes to tell you some of the things. I mean, these are things that I teach also, but then this is, I'm very passionate about, is sustainable development goals. And I want to tell you, and also the National Academy of Engineering Grand Challenge goals, which is 14 goals, 14 challenges like solar, health informatics, and both are very nicely connected. And I create all my STEM programs around these two things at all levels. And if a student comes asking me for a project, I ask them to pick a goal, and then I ask them what they want to do, and then the project comes from there. I'm not a faculty that just gives people projects. It's the opposite way. The student gives the project, otherwise I can't have fun in what I'm doing. So I'll give you an example in just a second. So I want to tell you about two recent projects, all how crime started evolving from this. I actually work in the area of infectious disease. This is one of the areas that I've been working on. And so good health and well-being. So everything that you're going through right now is COVID, by spread of, virus. So what happens is these models were classified as the SIR models. Now the S stands for susceptible people. For example, susceptible to COVID. And I are the ones that get infected, and then you quarantine them and they get recovered. That's the S, the I, and the R. So this was actually kind of documented by two students, Kermack and McKendrick, of a very famous Nobel Prize winner who tracked the path of malaria. His name is Ronald Ross. And they came up with these models called compartmental models. Now, not only did they come up with this, they also said the rate at which susceptibles become infected, the rate at which infected becomes recovered. By the way, teachers, if you're listening, I have games created for middle schoolers and high schoolers for this. But as you touch high school, you learn calculus. And so these rates can be written as differential equations. And you can actually connect the rate at which the susceptible population becomes infected. And so this is when the S meets the I and gets infected at a certain rate. That's the probability related to the number of times they meet and things like that. And the negative sign is because these guys move to become infected. Of course, I didn't include birth rates, death rates into this model. So from the differential equation models, then you would actually enhance the models. For example, there are diseases where there is no recovery. For example, syphilis, gonorrhea, and things like that, where you can become susceptible again. And then there are diseases where mosquitoes are involved. Good mosquitoes biting you, getting your blood, and then they get infected. Yes, there are something called good mosquitoes also, okay? So, but the mosquitoes don't get infected immediately. So they go through what is called as an exposed phase. Now, I'm writing a COVID model right now with my colleagues, and it's a mathematical model that actually includes the exposed phase, because you are asymptomatic. You don't know you have the disease before you start infecting people. So then an SCIR model is more appropriate, and we are tracking and matching the data that is real from the Hopkins websites and different things, and we are trying to actually go through this. And people interested in that topic, let me know. So what is interesting about things like Zika, which is different from malaria, dengue, chikungunya, and all that. I'll tell you why this is related to crime in just a second. Is not only does the susceptible humans become infected, but then notice that the vector, that's the mosquito, can actually go this way. So this so there's two types of transmissions. One is the mosquito biting you. That's what is called as the vector transmission. But then sexual transmission from humans to human, that is basically a direct transmission. The Zika was one of those diseases, unlike chikungunya, dengue, and malaria, where both were happening. So we have published this already as a mathematical model. And then not only did we do that, one of my former PhD students, if you want to look up the famous journal Science, in February 2020, just type February 2020 physics informed deep learning. You will see what the concept is about. But he and I have now introduced the concept for infectious diseases. And we are able to actually use the infectious diseases models to create deep learning neural networks to actually predict when diseases, when to flatten, when what the parameters should be, so that can help flatten a curve, for example, or when will things resume and things like that. And so we were able to also look at it from a statistical point of view as well as deep learning point of view. In fact, the reason it was published in Science is one of the fastest deep learning codes ever created. And in fact, not only that, for example, here's the infected data for 14 days from influenza that we selected, and we are able to predict everything else just with just the number of people that came into the hospitals, just using some kind of error measures and things like that. Again, it's a published paper. Those that are interested, you can ask. But what does this have to do with crime? Well, the student that did the Zika project with me, was sitting in the room, and a person from Puerto Rico came by and he asked for a project. And I said, pick a goal. And he said, okay, I'm interested in peace and justice. I said, why did you pick that goal? He said, oh, because my cousin got recruited into gangs. So that was a stumper for me, because I wasn't ready to actually model gangs because I didn't know where to start. And that's exactly when the kid that did the Zika and the kid that wanted to do this project actually started to talk. And they realized something very interesting. By the way, there's reports from Puerto Rico you can find in terms of the intensity of crime, different types of crime in everything from arson to different types of crime, plus the struggling economy too. Massive exodus. Maybe my faculty that I partner with in Puerto Rico is also listening in. It's been great that she sends these students, and we work together with these students. And so what we were able to create, it was not us. So we were just listeners. And these students came to us and said, Dr. Seshaiyer, we have an idea. And I said, what's the idea? They said, oh, we're going to take the population. We figured out who gets infected. We're going to make them two groups. One group is youth. Y is for youth. A is for adults. We're going to take the SIR model that I talked about. And they studied gangs as an infection. And basically they said, the youth in the house can become a gangster just by, it's like sexual transmission. Then I asked, what is sexual transmission? They said, oh, uncle in the house recruiting a cousin. That's like sexual transmission. That's proximity. Then I said, what do you mean by, what's the mosquito here? Well, they said, oh, that's like when you're walking in the street, you're lured into coming into gangs by adult gangsters. So they made sense of every single arrow that you have. From there on, as a faculty, what was my job? To teach them how to model this. Of course, I had to clarify certain things. I had to clarify where the data should come from and things like that. We were able to model it. I'm not flashing the equations, but you are welcome to read the paper to find it. Um, this work has not been published now. The one with deep learning, we have just employed deep learning on this. Hopefully, we'll be publishing this soon. It's tracking the number of infected people people and that is adults and children coming into police stations, and from that information we can actually backtrack and find out who's susceptible, who was recovered as in they went to jail and came out and things like that, prison and came out. But what we want to do is to overlay this with geographic information maps that we can create like ArcGIS or QGIS, and then we know something about Puerto Rico, and then we overlay our deep learning models, and then we are able to backtrack parameters that tell us where to focus on, what crime is going to happen where and things like that. That's in the works. This is the project that will complete this summer. And of course, as I said, it does impact policy because we were able to meet the governor, former governor of Puerto Rico. He was super impressed with the idea. We were also able to meet Mark Warner, Senator Mark Warner from Virginia, and he was very interested in learning about this. And we presented the work, and also, as I said, made an outreach program out of this for students. Another project that I'm not going to talk too much about, but this involves social dynamics. Again, because of a student, we were again able to go to the White House and talk to Senator Mark Warner about, she initially was disturbed by the fact that rezoning happens in Texas, and because of which she got her friends moved in schools and they lost their, ELL or English language learner teachers. And it was a big mess at one point. And so she wanted to study social dynamics. But the beauty is we were able to expand that to a crime model involving, some South America, like Mexico, Honduras, and Guatemala, and United States, how two populations, adults and children, move away from gangs, running away from gangs, or are stolen in. And so we were able to actually expand this model to study those types of models. Again, another idea of differential equations. My last thought for learning framework, I teach this concept. It's called design thinking. It's 5 steps, and you can start to type questions, please, and I'm going to finish in like 2 minutes. So these are very important concepts which goes through how do you empathize, how do you do the needs assessment, how do you actually do gap analysis, and from that you define all possible challenges that you want to address. But then you pick the challenge, the problem statement. Where most companies fail is not creating the problem statement, just solving the wrong problem sometimes. And then you ideate solutions. There's several ways you can do it. This is what I teach in my class, brainstorming strategies. You pick an idea that you want to go after, and then you prototype and test. So my final crime project that I wanted to show you, what is exciting to take a lot of students, is poaching in Africa, and specifically in Tanzania, where elephants are killed for their tusk. Each tusk is sold in the black market for 50,000 US dollars, and the rhino horns are about 1.5 million US dollars. So the question is, the empathy, of course, is, we jumped into the defining the problems. Who are the poachers? Where are the poachers? How do we find the poachers? And then we decided to go after the problem, like how do we find the poachers? And so we ended up going into drone. I had a team of students that were engineers, that were mathematicians. So I had to make sure that the project caters to all of them. And of course, the student that was geared towards mechanical engineering and mathematics, he studied motion. He talked about how the drone moves from one place to the other. He also talked about rotational aspects of it. And then we were able to come up with optimal control aspects of it and all that. And the student that were more interested in probabilistic ideas. So for example, if you know that there is a poacher in a certain area, how can you use something that you learned in middle school called conditional probability? Given that you know there is a poacher in this area, is the drone looking at a poacher or a ranger, supposedly a good guy, and or an animal? Well, then you think of warm-blooded versus cold-blooded. Well, if you distinguish between humans, how do you know if you're looking at a poacher or a ranger? Well, you see the type of guns they carry, because the different types of frequencies they emanate. For example, the rangers tend to carry pistols, and the poachers are carrying big guns for getting the elephants down and things like that. And then, of course, the heat can be sensed by thermal cameras and things like that. So it's about creativity at this point to really build that thing. It's an engineering concept, it's a math concept, bring a lot of probabilistic ideas and all that stuff, and create belief functions to figure out, is that a poacher, and should we be sending a drone there, or should we be going there, and things like that. So of course it has other ideas, because I'm a big proponent of STEM education. So this is everything from mechanics to control systems to swarming multiple drones, because you can't have a drone flying forever. You can only do for 20 minutes while you charge another drone at that time and then switch the ideas and things like that. So it is also published and you can actually take a look at it. And to finish, I think this is from last summer. I'm going to hopefully finish this project where how do you combine these ideas? You already saw how we combined it. So we went from a modeling idea of an infectious disease. We went on to a gang violence model. The last summer, another student came and said, Dr. Seshaiyer, I'd like to study opioids. And so we actually used the same type of idea to go from susceptible to prescription drugs to, getting addicted, basically. It's like infected. And then you get recovered, maybe recovered through technology and things like that. And then from there, how do you actually become an entrepreneur? That's the next thing that I wanted to get people to understand. So right now, think about a device that can be in your hand, and that device is tracking you all the time. And suppose you are watching TV, and on the TV comes a syringe, and you are interested to take drugs. At that exact instant, if all the signals that the device is captured sends based on a certain quantity, it calculates mathematical quantity. If it sends a signal to your cell phone, and your cell phone has your best friend calling you at that same instant and say, hey, let's go for coffee, or it's your mom calling, you just distracted yourself from that moment of going and taking drugs. So that's what we created. We've submitted a patent for this thing, which so I just wanted to tell you how we can go from a context to a curriculum that we create to the content that we'll develop to a concept. How do we do this in research? How do we teach this to competencies that we can create for students? And this brings up my last slide, which is like, as scientists, we are very, very inquiry based. We are always after a question. As engineers, we are always design based, which is like we are after a problem. And as engineers, we can build a small bridge and break it. But as mathematicians and as scientists, sometimes we can't break a microscope. So but we want to take the best of these two worlds: the inquiry-based approach to problem solving and the design-based, and then put them together to solve crime problems, for example. And I'm a big believer on don't just work on your own to solve a problem. You have to work in a multidisciplinary team. And more importantly, we need to change our philosophy of how we attempt to solve any type of problem, be it a crime problem, to go from, we tend to always go from, here is the mathematics, here is the content, let's go solve the problem. I mean, my challenge to you is to turn that philosophy to, here is the problem, let's find the mathematics to do it, let's find the physics to do it, let's find the engineering to do it. Now, try to do it that way. It's a challenge to your PhD. Okay, so it's a really interesting thing. I've learned it myself, I enjoy what I'm doing right now, and I'm going to finish here. Thank you. Thank you for listening to me very patiently.